Welcome to Module 3 on exponential equations. We're going to start this module with an example. It says, consider the following table of data representing the number of stores for company A and the number of stores for company B. You can see all the data is represented in this table. We have a certain number of years that have gone by, so after 2 years, after 4 years, 6, 8, and 10, and so on. And then we have the number of stores for company A and the number of stores for company B. This is very similar to some data that we would have seen in the scatter plot Excel lab, except for now we're plotting two sets of points. So we have your time variables, so along the horizontal axis, and then we will plot the y values for company A and the y values for company B. This results in two different curves being shown on the graph below. So we want to look at the data as well as the graph that's provided and determine which of the graphs represent company A and which represent company B. A key thing to recognize is that each of the curves represent the data in the table above. And after 2 years, we know that company A and company B both have 200 stores. So we know right here that the number of stores is approximately equal to 200. And we can actually put some more information. This is number of stores. And then this is time in years. As we look at further time down the road, so beyond 2 years, we know that at 4 years, both of the companies have 300 stores. Then after 6 years, company A only has 400 and company B has 450. So company B has a greater value. So we would anticipate that the top curve would be for company B. So we continue again to 8 years. We have 500 for company A and 675 for company B. So it's safe to say that we can label the red line, the top line, as company B and the bottom line as company A. Although the number of stores in the second and fourth years are identical for company A and B, you can see that that trend does not continue beyond 4 years. And when we examine the table above, you can see that when we look at the values for company A, each and every single year, we are increasing the number of stores by 100. A constant increase that company A exhibits is what you call a linear equation. It would produce a linear equation as we looked at in Module 1. Whereas company B can be seen to increase by a certain ratio. So if there's a value, you can multiply each of the previous values by to arrive at the next value. And that value is 1.5. So we're multiplying each and every single value by 1.5, a common ratio, to arrive at the next value. And that is what you call an exponential equation. There are many applications in science which involve exponential functions. Some of these examples are growth of bacteria in a lab, decay of radioactive material, spread of communicable disease over time, and many more which we'll be exploring in future videos. The general form of our exponential equation is as follows. We have y is equal to b to the power of x, where b is a constant. A constant is simply a number that does not change, whereas x is our variable, and notice it is in the exponent. So we have b is the base of our exponential equation, and x is our exponent, which is a variable. There are restrictions on b, and b cannot be equal to 1, and it must be greater than 0. So it can be larger than 1, but can never equal 1 and can never be negative. We'll see the reason for that as we explore these functions. Here are some examples of exponential graphs. We have y is equal to 3 to the power of x, where b would be equal to 3, and we have our exponent variable x. Y is equal to 1/2 to the power of x. So again, our b value, our base, is 1/2, which satisfies the requirements that it's not equal to 1 and it is greater than 0. And we could also have a constant such as pi to the power of x, or the square root of 46 to the power of x. Now we're going to look at graphing exponential equations. First, we're going to graph y is equal to 2 to the power of x. We can label the first row with our x values and our y values. Similar to our unit on linear equations, we're going to examine the table of values using 5 different points by considering some positive and negative values, as well as 0. The first point we're going to examine is for x is equal to 0. Okay, that will give us our y-intercept. And when x is equal to 0, we plug in 0 in for x. You get 2 to the power of 0. And you can calculate that in your calculator, or know from exponent rules that anything to the power of 0 is always equal to 1. For x is equal to 1, we get 2 to the power of 1, which is 2. 2 squared is 4. 2 to the power of 3 is equal to 8. And when we look at negative values for x, 2 to the power of negative 1 is equal to 1/2, or 0.5. And 2 to the power of negative 2 is equal to 1/4, or 0.25. So now we'll plot each of those points on our graph. We first label the x and y axis, and we know that we need to have y values ranging from 1/4 up to 8, and our x values will range from -2 to +3. We can plot each of the points, so we have 0, 1, 1, 2, 2, 4, 3, 8, and on the negative x-axis, we have -1 and 1/2, -2 and 1/4, and so on. Now, connecting each of those points with a nice, smooth, continuous curve, we get the following exponential graph. Looking back at our equation, y is equal to 2 to the power of x, notice that our value for b is equal to 2. And that value of b expresses what occurs from one point to the next in our table of values. So it gives us our ratio. And at each increase in the amount of time, we are multiplying by 2 to get the next value. In order to calculate each of the values in the table of values, you will need your exponent key. And depending on your calculator, every calculator is a little bit different. So some calculators may appear with a little hat. Others are y to the power of x. There's also x to the power of y. And some calculators even have x to the power of, and have a little box shown where you type in your exponent. So use these values provided in the table of values along with your calculator to make sure that you know how to calculate the value of an exponential equation, and ask for help if you're having difficulty. The second example for graphing an exponential equation is y is equal to 0.25 to the power of x. We're going to graph this exponential equation using a table of values. So we have our x values ranging from -2 up to 2, and our y values, or y is equal to 0.25x. Pause the video now and calculate each of these y values. Now that we've filled out our table of values, we can plot them on the graph. Now that we've plotted all the points on the graph, we can connect them using a smooth, continuous curve to represent the graph of the function y is equal to 0.25 to the power of x. Looking at our original equation, we see that b is equal to 0.25, which is 1/4, and looking at our table of values, we can find subsequent values by multiplying by b, so multiplying by 1/4, which can also be thought of as dividing by 4 to get from one point to the next. Some key notes to make about these graphs. In the first example, where we had a b value greater than 1, we can see that y is increasing. So take a look at this curve. As x increases, so over time, y is also increasing. Whereas in the second example, we had a b value that was between 0 and 1, and as time increases, our function is decreasing. Our equation value of y is decreasing. Okay. Also, you can see that the graph approaches but never touches the x-axis. Therefore, it has no x-intercept. It's never going to cross the x-axis. So for example, as the graph for y is equal to 0.25 to the power of x, as x increases, we get closer and closer and closer and closer and closer to the x-axis, but it will never cross the x-axis. And the same holds true as we look at the values of x and we decrease them for the first function, y is equal to 2 to the power of x. We can see that the values will keep decreasing, but will never cross the x-axis.